At this point, we've cached out our fractured geometry, and now we can do some more optimization of this and build some proxy geometry that will be more lightweight for interacting with in our scene and also what we will want to ultimately simulate. And in order to start working on those fractured pieces, we're going to need to do an RBD unpack to get access to those, because right now our cache is just bringing in 3 packed container objects. One of those is the fracture objects, and one of those is the constraints, and the third is for the proxies that we're not using yet. So those were packed up with RBD pack before, and now we can get access to those again by doing an RBD unpack. This will give us all of our fracture geometry and constraints and proxies out of those 3 outputs. And as we're optimizing this fracture here, we want to reduce the number of pieces and get rid of some of the really tiny ones that we don't want to include in the RBD sim, but we have to be a bit careful about it because we don't want to ruin the look of the exterior of the surface, so we can't remove too many pieces there, but on the interior we can remove far more pieces without it messing up the look of our geometry. So after our RBD unpack, let's drop in a split, connect that to the first output of that RBD unpack, and we're going to isolate the exterior pieces by using that inside only attribute. So say at inside only equals 0, which we had derived earlier from the inside attribute when we did an attribute promote on that. And if you display that split SOP, this gives us all of our pieces that are touching the exterior. And now we can just do a blast to remove some of the tiny ones based on the area attribute that we've already set up. So let's display that blast, and for the group I'll say at area is less than 0.5. So right now this is removing a fair number of pieces, and it's ruining the look of the exterior of our surface here. So let's start playing around with this area cutoff to find out what size threshold we can use to reduce some of the pieces without ruining the look here. So I'll try 0.1, that's still removing quite a few pieces. 0.05 is still showing some artifacts. 0.1 is probably okay, or I should say 0.01. There are still some little problematic spots that might not be too visible in the render. Sometimes you might need to render this to see if your surface is intact enough or not, but I'm going to be pretty conservative with my area threshold here. I'm just going to set this quite small to like 0.004. And I think this will be fine. This shouldn't be messing up the surface of our geometry too much. Some of these little artifacts will probably be less visible in the render than they are in the viewport here. And if you want to see the actual pieces that are being deleted, we'll just flip this blast to delete non-selected. And you can see these are all the tiny little pieces that are being removed by our current size threshold. Now let's make a copy of this and attach it to the second output of that split, which I'll rename to split exterior. And then for this second blast, we can delete more pieces than we were before. So for this size threshold on the inner pieces that aren't touching the exterior, let's raise this value quite a bit higher. I'll about double that to 0.01. And the pieces that this is removing are still quite tiny, except for this large one here, which we'll have to take a look at in a moment, because that might be an error in the area calculation or something. But I won't worry about that for the moment. Let's try an area threshold of 0.1 for this. So the pieces being deleted here are quite a bit larger than on the exterior, but this is totally fine since we're not really going to see this in a way that the surface really needs to stay intact. So let's turn off delete non-selected to see what's left over. Do the same thing on the exterior and then merge these together. And after that cleanup, we now have about 6,600 pieces. Before we did this cleanup, we had almost 13,000 pieces. So these 6,500 pieces are going to simulate much faster, they're going to render much faster caches will be more lightweight and it'll be much easier to work with overall. And visually, there's really not much difference between this cleaned up geometry and what we see when we display our RBD unpack. So we're really not losing anything visually by cleaning up all those tiny ones. Now we were seeing something a little bit strange when we did the cleanup for the inside pieces. So let's flip that back to delete non-selected. And it looks like there are a couple larger pieces that may have some incorrect area values on them. And I'm not too worried about it if we remove those, because this is just on the inside of that fractured geometry, so we won't really see it as a problem, even if we delete these larger pieces. But I'm just going to investigate them a little bit further anyway. So let's go into selection mode and select based on the name attribute. Although in this case, we don't have the name attribute available in our primitive attributes here. When we did the assemble on our geometry earlier, this packs up the fractured geometry and it does preserve the name attribute, but it moves the name attribute from primitives on the raw polygons onto points for the packed pieces. And I imagine this is largely because a common use case for packing up geometry like this is often to use it for a rigid body sim. And rigid body simulations in Bullet need to have their important information on the points. So that's my best guess as to why they moved the name attribute from primitives to points there. But that means that when we're selecting this piece later, based on that name attribute, we can no longer pick it from our primitive attributes list here. We could instead go to point selection mode and then select the name point attribute here, although it's a little bit more challenging to select objects, especially when it's a whole bunch of packed pieces like this, based on point attributes, because you really have to select based on the actual point at the center of the object, and it can be a little bit difficult to select that correctly. So sometimes when I'm in this situation, I like to make a separate name attribute that's on the primitives. This is really just an optional step. It's up to you if you want to leave this attribute on the geometry or not, but we can do an attribute promote. Original class is point, new class is primitive, original name of the attribute will be that name attribute, and promotion method doesn't really matter, maybe just pick first match. We don't want to delete the original, and I will change the new name to name_prim. So then I suppose we could put this name_prim attribute just after the RBD unpack here. And now going back to our filtered out results here, if we go into our selection mode again, go back to primitive selection based on attributes and then select the name prim attribute here. Now you can see it's a lot easier to select things in the viewport. This is something I do almost all the time when I'm doing destruction work, because I do tend to do a lot of manual selections to really art direct what different portions of the geometry are doing, and it's much easier to select things this way. So let's select this one piece that we're interested in checking out here to see why this large piece is being caught by our small piece filter. So let's delete that to drop in a blast stop, flip it to delete non-selected, and take a look at the attributes on this. This is reporting a very small area on this packed object here. So let's unpack it and look at what's going on the underlying geometry and check out that spreadsheet. And this is a little bit strange because this piece has the same piece name for all of the primitives here, but strangely we're getting two different area values. Now the area calculation that we did earlier was a per piece calculation, so each individual piece should have the same area values on all of them, but that's not the case here. So I wonder if this is a legitimate bug, but in any case we do have workarounds here. So let's close that spreadsheet, and I'm going to grab this same blast stop and bring it up earlier to where we did our area calculation. And let's drop in this blast stop to check out that one piece. Although at this point, this just has that standard name primitive attribute. So I'll change this blast stop to, instead of deleting based on the name prim attribute, we'll use the standard name attribute. So we're isolating this one piece just after the measure stop earlier. Once again, we're seeing the same strange thing happening on those area values. If we look at the measure stop, you can see it really should be accumulating one value per piece, but since this is not working, let's try something slightly different. We'll set the accumulate method back to per element, which is no longer doing any area accumulation. It's giving us just the area of each individual primitive on our geometry. But then afterwards, we can add up all of the area values per piece. And if you remember from an earlier video, we calculated this inside only attribute based on promotion within each individual piece specified by the name here. And to get inside only, we checked the minimum value of the inside attribute of every piece. Now we can do something similar to calculate the total area from the area measurements of each individual polygon. So after the measure, I'm going to right-click that output and type in promote to drop in an attribute promote after our measure. Original class is going to be primitive. New class is also primitive. Once again, we will promote based on a piece attribute called name. The attribute that we want to promote is area, and we don't want to calculate the average area of all the polygons in each piece. We want to sum them all up. So for the promotion method, select sum, and I'll rename this attribute promote sum of polygon areas. And now checking our problematic piece once again. If we look at the spreadsheet after doing the sum of the areas on all of its polygons, now we're getting a much more reasonable value. And if we compare that to what we were getting before, now this new summed up area makes total sense. The ultimate area of this piece is the sum of the two areas that we were getting on that problematic version that was working incorrectly before. So it looks like this fix for the area calculation is working properly. So after fixing that, let's rerun our cache of the fracture. I'll save that to disk. And now if we take another look at our filtered small pieces, now we no longer have those big ones mixed in that made it pretty clear that something wasn't working properly. Both of these size filters look all good now. Now another thing to watch out for when doing some optimization like this is that you may want to delete the constraints for the pieces that were removed. I don't know how much of an impact this would have on the bullet solver if you leave all of the constraints for the missing pieces. In my experience, it doesn't actually break anything if you leave the constraints in there that don't belong to valid pieces in your simulation. Things will still work properly, but it's still good to make sure you clean up everything along the way, even if it doesn't explicitly stop your simulation from working. So there's one interesting way that we can delete all of the constraints that were attached to those small pieces that we deleted. So one technique you can use to do that cleanup is to create an attribute on all of your existing fracture pieces here. I'll drop in an attribute create, and I'm calling this attribute exists. This will be a point attribute of type integer, and let's write a value of 1 and leave a default value of 0, and connect our optimized fracture geometry to that. And now we can do a transfer of this exists attribute onto our constraints. So let's do an attribute copy, connect the constraints to the first input, rename that null constraints, and then connect our attribute create for the exists attribute to the second input of that attribute copy. For the attribute name here, we'll select that exists attribute, and we want to match by an attribute as well, so that constraint points with a name that matches the name from our fracture geometry will get that value copied over based on that matching name attribute. So for this attribute copy, turn on that match option. Attribute to match by will be name. And this will copy this exists attribute onto the constraint points here. However, we don't want to just delete constraint points, we want to delete the constraint primitives. And I want to delete constraint primitives if either end of the constraint line corresponds to a piece that no longer exists. So let's do an attribute promote. Select this exists attribute, promote that to primitives. Promotion method will be minimum. And this ensures that if either one of the pieces at either end of the constraint doesn't exist, then this exists attribute will pick up a value of 0 for that entire primitive line. So after that promotion, let's just drop in a blast stop and say at exists equals 0. So let's zoom out, and if you flip this to delete non-selected, you can see all of the constraints that are getting cleaned up because they're constrained to a piece that we've deleted from our fracture. So this is deleting 16,000 constraints here. Turn off delete non-selected. That's leaving us with 16,000, so nearly the same amount. So ultimately we've cut the number of constraints in half. So now let's drop in a couple nulls to keep our scene nice and clean. I'll call this constraints optimized, and we'll drop in a null for our fracture optimized as well. And we can pack these back together with our RBD packsop. Fractures in the first input, constraints in the second. And now we can take a look at generating some proxy pieces for our fractured geometry.